In this video, you'll learn how to use the Horiba LabRAM Aramis Raman Microscope in the Inorganic facility at the Molecular Foundry. If you're being trained on this microscope, the idea is that you would sit at the microscope and follow along with the video, first using a piece of silicon and then using your own sample.
So this is the Raman microscope. It's a self-contained microscope. You don't need any extra laser training because it has interlocks. These doors open up the Raman chamber, and you can see it's an Olympus microscope that has actually two different stages stacked on top of each other. So this bottom stage is a motorized stage, and it's good for very large movements that you would control using this joystick. And then on top of it is a piezo stage, which can make very small sub-micron movements, and that's good for mapping. The first thing that you want to do when you get to the Raman is find this handy manual, which you can also find online in PDF format. So this is not the full manual. You can find the full manual on the desktop of the Raman computer. But it actually has most of what you need to know if you just need to take a spectra or a simple map. The first thing you want to do when you get to the Raman microscope is to open up the overview, because it'll tell you all the individual steps you need. The first step is turning on the instrument. Now, we don't actually turn off a lot of devices for the Raman microscope, so it's actually pretty easy. Mostly what we want to do is turn on all the light sources.
The first light source you want to turn on is the white light lamp. This is located underneath the laser table. This lamp provides the white light that you use to focus on your sample.
Most people use the reflection lamp. You see there's the transmission lamp and the reflection lamp. So it's hard to see, but there's actually a button on the bottom side of this lamp. And so you're going to turn on that button. So now there's white light going through the fiber optics. So most of the time, this reflection lamp is on the setting 3 for the left knob and E for the aperture. You never really want the temperature of the lamp to go much above 2900 Kelvin unless you have a really dark sample, say like a mat of carbon nanotubes. If you leave the lamps on full blast, then they'll pretty much die in a day or two. So you really want to make sure that if you do turn up the lamp, you turn it back down to about the setting of 3 or about 2900 Kelvin. The other light sources you want to turn on are the lasers. So the lasers are found to the right of the Raman microscope. So the top laser is 532 nanometers, the middle laser is 1064 nanometers, and the bottom laser that looks a little different is 785 nanometers. The 1064 laser is really not used for Raman. We've set it up to do anti-Stokes luminescence or upconversion luminescence. So 532 is by far the most commonly used laser. That's because it has much more scattering than, say, 785 nanometers. But you would use 785 nanometers if you're having a lot of trouble with fluorescence or damaging your sample. 785 nanometers has less energy than 532, although you need a higher power to get the same amount of scattering. To turn on the 532 nanometer laser, you're going to first turn this key. And so when this red light starts flashing, then you're going to know that you can activate the laser. So this key only turns on the power to the power supply, whereas pressing this red button will actually turn the laser on. So when you hear that beeping, the laser turns on. So you should never mess around with these knobs or the menus. In principle, you can change the power of the laser at the box, but it's not a great idea because whenever you change the power of the laser at the device, you could change the alignment, you can change the temperature. It's much better to change the power of the laser by introducing, for example, neutral density filters. The 1064 laser is the same, but again, most of you are not going to be using it for Raman microscopy. The 785 nanometer laser is a little different. So we're going to press this power button here to turn on the power supply, and you're going to let the splash screen open up. To activate the laser, you're going to press this lower on-off laser button. So now you can see that your actual current is very similar to your set point current. Today, for this training, we're going to measure the Raman spectrum of silicon. It's a good sample for you guys to start with, and it's a baseline sample because many of you are going to run your samples on silicon. But the other reason why you want to know how to measure silicon is because if you can't take a Raman spectrum of silicon, there's something really wrong with the microscope. So before you come running to me or the super user complaining that the Raman microscope is not working, you should run a spectrum of silicon. Inside the microscope, usually inside the doors or just under the microscope, is a sample, a glass slide that has a piece of silicon taped to it. So the first thing I want to do when I load a sample is to actually make sure that there's enough clearance for me to go in there and stick my hand into the microscope. And so the first thing I would do is I would turn the turret of the objectives so that the shortest objective is now activated. So I'm always grabbing the turret by this knurled ring. I don't want to grab the objective because I don't want to get whatever's on my glove or on my hands onto the lenses of the objectives. So this gives me a little bit more clearance, but I also want to have even more clearance, so I'm going to lower the stage using the Coarse Focus knob. So the Coarse Focus knob is found on the left side on the bottom part of the microscope. And so I'm going to just lower the stage gently down to the bottom. So now you can see I have a lot of clearance in between the objectives and the stage. So then I'm going to take my slide and then I'm going to put it here onto the top of the piezo stage. Now, if you take a look, it's not that apparent even in person that the stage is hollow. You can actually stick your finger all the way through the stage. And not everybody knows this. So you really do need a long glass slide to span this gap, or else if you stick your precious sample down in the middle, it's going to fall to the bottom. It's pretty annoying to fish out your sample from that hole. You have to take apart all the stages. Once your slide is on there, you would want to start looking at that sample through the microscope. So the next thing you need to turn on is you need to open up the LabSpec software, which runs the Raman microscope. So the icon for the LabSpec software is located here on the desktop of the Raman computer. If you have a security message, just say yes. The LabSpec software can take a little while to load up. LabSpec will initialize in the beginning, and then it'll show you this splash screen. So occasionally, the software gets in a state where no matter how many times you double-click the icon, the software won't open. So the solution to that is just to restart the computer. The password is located on the front cover of the logbook. The first thing you need to do in order to look at your sample is to turn on the camera icon. When you turn on the camera, the shutter for the white light will actually open up, and you can see light go through the objective. So otherwise, there is no light going on to your sample. So to move your sample under the microscope, you can move the sample using the joystick until you're focused just about on the edge of the silicon. Now, you want to focus on the edge because it's easiest to get contrast. Now that I've gone to the edge, I'm going to use the coarse focus, which again is on this left side of the microscope. I'm going to slowly bring up the stage. So you can see that when the front of the knob is moving up, the stage moves up, and when the front of the knob moves down, then the stage moves down. Now, a good rule of thumb is that when I'm on this really short 20x objective, the working distance is about 2 finger widths wide. So if you're closer than 2 finger widths, there's a problem. And this is important because the worst thing you can do with this microscope is to crash the objectives so that the objectives hit your sample. That's bad not only because you could potentially damage the objective and get your sample on it, but also you can misalign the microscope. And so for a confocal microscope, alignment is very important for getting signal. So as I move the objective up and down, as I get closer to focus, the point of light focused on my sample will get smaller and more intense. And as I move away from focus, then the point of light will actually start getting bigger again. So you want to minimize that point of light while also watching to make sure that you don't hit your objective onto your sample. As I'm moving my sample up towards the objective, trying to focus, I'm focused on looking at the sample so that I know that it's not hitting the objective, but I'm also looking at the screen of the computer to see whether there's actually anything coming into focus. So I'm looking back and forth without losing sight of one or the other. And this is really important. So when you take your checkout test for the Raman microscope, this is the most important question that I'll ask you. Now, if you're looking at the screen, what you'll see is that when you're far out of focus, the screen will look black. The camera image will look black. But as you get closer and closer to focus, the image will start to get brighter, and ultimately you'll start beginning to see features. Now, if you're focused on the edge, you'll see a very high contrast between your silicon and the background. So that's why you want to focus on the edge, and sometimes you have to actually start adjusting the position of your joystick so that you make sure that you're right on that edge. As I start to see that the features are in focus, I can navigate around using the joystick until I find the particular spot on my sample that I want to take a Raman spectrum. Usually you don't want to take a Raman spectrum with the 20x objective. And that's because the 20x objective has a very small numerical aperture. So that means it doesn't collect very much light. Typically people like to use the 50x long working distance objective. So that's the objective to the right of this very short 20x objective. And so again, you're going to rotate the turret using the neural ring, and you're going to wait for the objective to snap into place. So if you don't feel a little click, you haven't gone far enough. And it'll be really obvious in your image. If you see a very non-uniformly lit image, a lot of times the problem is that your objective is not seated properly, that you haven't let it click into place. So at this point, you want to close the doors of the Raman very gently. Gently because this is a sensitive optical instrument, and anytime you bang on the instrument or you're leaning on the table, you could actually change the alignment with the microscope, or you could also bother the cryostat measurements that sit right next to the Raman microscope. When you close the door, you hear this click. And that click is the interlock that controls the shutter of the microscope. And so when you have the doors open, the laser shutter is preventing the laser from coming out and shining into your eyes. But when you close the door, then the shutter can open up, and you'll often see a laser coming onto the video camera view. Now, when you change the objectives, your focus should be fairly similar between the objectives, but because you're at a much higher power, a little bit of out of focus will seem a lot more with a higher objective. Importantly, when you use the 50x objective, you're not going to use the coarse focus, right? So you can see that you're closer to your sample, and when you actually use the 100x objective, you're really close to your sample. So you don't really want to use the coarse focus because you could very easily run into your sample. And people have crashed the objective so hard that the glass slides have broken. So that's not what you want to do. So instead, you're going to use the fine focus. So the fine focus is done by rotating this joystick. And we set it very sensitively so that a little bit of rotation will start moving the objective pretty fast. Start by just moving the knob very slowly at a very low angle. And then once you get the hang of it, you can start getting more adventurous. Some people, like if they want to move the focus really small distances, will just flick the objective until they get it into place.
So when you're focusing, you can focus on features in the white light image, but it's actually more important to focus the laser because that's what's scattering and giving you your Raman signal. So when the laser is small and intense, that's when it's at its most focused. So after you've focused using the white light image, make sure that you focus the laser. So now that we've focused the laser on our sample, it's time to set up the spectrometer. So all of the spectrometer settings are located in the bottom toolbar of the software. So in general, we're going to go left to right in this toolbar to set all of our settings. So we'll first set the laser wavelength at 532 nanometers by clicking the down triangle of this pull down menu. So 532 nanometers is the first wavelength you should choose because it has the most scattering. Note that external laser means the 1064 laser. If you want to use the 785 laser, you should choose laser 785. The laser 785 PL is not used. Moving to the right, we'll set the filter next. So the filter filters out the laser before it hits your sample. And it's in units of optical density. So ND4 means a power of 10 to the negative 4 times the power of the laser without a filter, while ND of 1 means 1/10 of the power. I like to use an ND of 1 for my first try of imaging, but when I'm trying to focus the laser, I use an ND of 4. Now for samples that are particularly beam sensitive, you might want to try a higher ND filter so that you don't damage your sample, and you can always go up if you don't get enough signal. Next, we'll set the pinhole size for the microscope. The pinhole is responsible for spatially filtering the microscope image so that only the signal from the focal plane is collected. For taking general spectra, 200 microns is a good pinhole size, whereas for mapping, 50 microns is best. Remember to press enter after typing in the pinhole size so that the motors actually move. If you don't press enter, the system will stay at its old pinhole size. We're going to actually skip over the spectrometer setting and move on to the grading, which is one spot over. The grading determines the spectral resolution or the wave number resolution of the Raman spectrum. The higher the grading, the better the resolution, but the narrower the range of your spectrum. 1200 grooves per millimeter is a good general purpose grading, while 1800 grooves per millimeter will give you higher resolution, but at the expense of a narrower wave number range. People measuring carbon-based materials such as graphene like to use the 600 grading because it has a wide wave number range that allows them to see all their peaks without having to take multiple spectra. Each grading is also optimized for a different wavelength, so for more details, please see the appendix on the gradings at the end of the manual. The field below the grading is the microscope objective. This doesn't actually set the physical objective on the microscope. You still have to do that manually. So this field is more of a record-keeping feature where you're supposed to select the objective in the software, in this case, the 50x long working distance, to match what the microscope is actually set at. This is important because it allows the software to set the proper scale bar for the image that you see on the screen. So when you set the objective, you'll get a dialog box asking you to confirm that you set the objective on the microscope to the same objective that you set in the software. The field below the objective is the file name or file prefix. Every time you save or acquire a spectrum, it will name the spectrum with this prefix and then append a number at the end. So you can name this whatever you want. We're going to name it silicon training. Moving back to the spectrometer settings, we're going to set the wave number that will be the center of your spectrum. So if you know that you have a particular feature that you want to look at, for example, silicon has a feature at 520.7, then you'll just type that wave number. Now remember to press enter after you type that wave number, otherwise it will go back to the old settings. So you can tell that the grading is moving because when you press enter, the numbers will change very quickly until they settle on a number that's close to but not exactly at the wave number that you typed in. Next, we'll set the acquisition parameters for our spectrometer. So normally when you want to acquire Raman spectra, you first want to see what they look like before you take a very long spectrum with a lot of averages. So this preview is called real-time display in LabSpec. And this target icon shows you the exposure time for that real-time display. So you want to keep it kind of short, like 0.5 seconds, unless you have trouble getting decent spectra otherwise. So the field below the real-time display, this clock icon, is actually the acquisition time for taking a permanent spectrum. So normally you might want to take this for a longer amount of time to get better signal to noise. But you should not make this so long that you saturate the detector. The detector will saturate over 50,000 counts, or at least it will become nonlinear in that regime. So if you need better signal to noise above that integration time, you can also average more spectra. And so if you set a number of averages or an accumulation number of 3, then you'll average 3 spectra. I like to keep my acquisition times pretty reasonable, anywhere from 1 to 10 seconds. And then if I need to get better signal to noise, I'll just average more. To the right of the acquisition settings are the stage settings, or the stage coordinates. In this case, it's showing the piezo settings, which you can tell because it says XYZ PI. So these XYZ coordinates tell you the current coordinates of your sample. They're not so useful if you're just trying to take a single spectrum, but if you have a certain feature that's 10 microns away from an alignment mark, you can focus on the alignment mark and then type 10 in the x coordinate and move 10 microns over. Likewise, if you want to focus or defocus by a certain amount and then go back to the old focus, you can type numbers into the z coordinate. To the right of the XYZ settings are the Z motor settings. You should never touch this. This could really damage the microscope. And to the right of the Z motor settings are the Aramis settings. The top button is the laser shutter. If you click on this laser shutter button, it will open and close the shutter, which will allow laser to hit your sample. So if your camera's on, you can start to see the laser light up the screen. Note that when you're looking at the laser with the camera, you should use a higher ND filter, such as 3 or 4. So now that we've set up the Raman spectrometer, we're ready to take some Raman spectra. Before you take any spectrum, it's important to click the stop sign button if it's dark and red. This indicates that the camera is still running, and importantly, the camera controls the white light shutter. This is the lamp light that you use to focus on your sample. But if you actually take a spectrum while the white light is entering the microscope, then you'll just get a spectrum of white light. People forget all the time, and you end up seeing a really broad spectrum that has way more counts than you really should be seeing. So if you see that, just click the stop sign. This stops whatever process happens to be in progress, and then restart taking your spectrum. The next thing you want to do is preview your spectrum using the RTD, or real-time display feature. To take an RTD spectrum, click on the target icon in the upper toolbar. The spectrum window will pop up and automatically display the spectrum of your sample. The spectrum will be continuously refreshed according to the RTD acquisition time that we said earlier. In this case, it's 0.5 seconds. If your signal seems low, particularly at the zero loss peak at 0 wave numbers, decrease the ND filter to increase the excitation power at your sample. You can see that the y-axis numbers have changed to reflect the fact that the peak intensity has increased. You can see in the spectrum that there's a lot of the spectrum devoted to the negative wave number region, which isn't really useful since there's a long pass filter that blocks any light below 80 wave numbers. To view more of the useful part of the spectrum, we can recenter the spectrum by typing in a new center wavelength in this spectrometer box. You can do this even while the RTD mode is still going on, so you can play around with the spectrum live. To stop the RTD acquisition, click on the stop sign icon, which will stop any process that's happening on the microscope. The left vertical toolbar has a lot of nifty tools that you can use to manipulate your spectrum. For example, this arrow icon can be used to place a cursor on the screen, and you can read out the coordinates of that cursor on the bottom right-hand corner. So S would be the x-axis, and I would be the intensity. To zoom in on a region of your spectrum, you can click on the magnifying glass icon in the left toolbar and then draw a window for the region of the spectrum you want to view. If you want to autoscale or zoom out to view the entire spectrum, you can click on the crosshair icon in the top toolbar. Now that we're happy with our spectrum and settings, we can actually go ahead and acquire a real spectrum. To do this, we're going to use my favorite button in all of scientific software, the piggy bank. So technically this button is called spectrum acquisition, and you can see that in the tooltip, but for now on we're going to call it the piggy bank, and that's what everybody in the lab calls it. So you can see that this icon has an image literally of a piggy bank with a coin that has a spectrum on it, so you're literally saving a spectrum. When I click the piggy bank, the software takes a spectrum with the acquisition time that you set down below, and it repeats that however many times you set it to average. So the spectrum will update as it's taking each replicate spectrum. If you want to change the intensity, maybe because it's too high or too low, you can change the acquisition time. So here we're going to change the acquisition time from 1 second to 0.5 seconds. And you can see when you do that, the intensity will change, or it's decreasing by half. So now that we've taken 2 spectra with the piggy bank, we can see on the right-hand toolbar that we have 2 different colored circles that represent the 2 different spectra. If you want to just view one spectrum at a time, you can click on the 1 button here on this right toolbar, and then you can click on the colored circle that represents the spectrum that you want to see. If you want to go back to seeing all of the spectra, you can click on the plus button. And if you want to actually exclude certain spectra from this multi-spectra view, you can control click on the circle of the spectrum that you don't want to see. Here's a final tip on taking spectra. If you want your spectral range to be broader than the range you get with a single spectrum, you can use what's called extended range mode, which you can access by clicking this icon that looks like 3 different bumps. So in this extended range dialog box, instead of using the mode called single window, you can actually choose the mode called multi-window, and then you can select the start and end wave numbers of your spectrum. Then when you click the piggy bank, it'll actually take multiple spectra that span this wave number range, and then those spectra will be automatically stitched together. Note that you can only do this using the piggy bank option and not RTD. Remember to turn the extended range mode back to single window so that you don't confuse the next person who tries to take a spectrum. Now, despite the fact that the piggy bank makes it look like you're saving the spectrum, the button doesn't actually save your spectra to the hard disk. It only saves it to the local memory of the software. So I highly recommend that you actually save your spectra to the disk. And to do this, you're going to click on the circle that represents the spectrum that you want to save, and then you're going to go to the File menu and select Save As, or you can click on the Disk button. I recommend that people save their spectra in 2 different formats, so actually save their spectra 2 times. You should first save your spectrum as a LabSpec format, and this is because this format actually saves all your settings. The hardest part about starting to do Raman on a new material is optimizing all the settings, such as the laser wavelength, the laser power, the grading, and the integration time. If you don't want to record all of that in your notebook manually, the easiest thing is to just save this spectrum as a LabSpec format. When you open up a LabSpec file, then you can click on this I button and see all of the different settings that you chose before. This is also good for being more reproducible when you come back and do a new sample on another day. So of course, the LabSpec format is proprietary. You're not going to be able to open that up in your own graphing software. So I also recommend saving as a text file. Keep in mind that the text file doesn't save any of the settings. Also, make sure to check this axis button so that you save both the X and the Y axis in your file.
So when I'm done with my sample, I can open up the doors gently. I'm going to change the objective back to the low magnification 20x objective just to give myself a little clearance. That's nice because if I accidentally move the stage the wrong way, I have a little bit more room for error. So after I change the objectives, then I'm going to lower the stage. And after I lower the stage, I can take out my sample, and then I can put another sample back in here. So when I'm done for the day, I'm going to close up the Raman chamber. I can clean up this area, and then I'm going to turn off all of the light sources. So I'm going to turn off the white light lamp. Again, I'm going to make sure that it's set at about 3 for the left knob, and then I'm going to turn off this source, and then I'm going to turn off all the laser sources. So the lasers, you don't actually have to turn off the laser and then the power supply. You can just directly turn off the power supplies. So you also want to close all the windows
of the LabSpec software, you don't have to close the LabSpec application, but you want to close all the individual windows inside the application. The reason why you don't want to close the application is that sometimes the LabSpec software has trouble starting back up. So the last thing we need to do before we leave is to sign the logbook. So the logbook is usually sitting right next to the Raman microscope or on top of the Raman microscope. And so we can write down the date, your name, your user project number, the time, which lasers you used, and any notes. So notes include, did you calibrate the microscope, and which gratings did you calibrate? Or if you had any problems, you should note that. But you should also email Emory or the other super users to let them know if you had a problem.
That concludes our Raman training. As a reminder, please do not crash the objective. And when you're done, please turn off all of the light sources, especially the white light lamp. When you're done, please also set all of the settings that you changed back to their default state so that new users don't get really confused when you change a very minor setting. If you're having issues with Raman, feel free to call, text, or email a super user using the phone number on the front cover of the manual. At the end of your session, please sign the logbook, and before every new session, reserve the instrument on the Foundry's calendaring system. Finally, we didn't have time to cover many of the advanced features of the microscope, so please contact a super user or come back to this channel for additional training videos on calibrating the spectrometer, Raman mapping, using the near-infrared detector, measuring liquid samples in cuvettes, and many other software features.